Okay, so this is exciting. We are, by the way, about halfway through all the material for this chapter, but we've got lots of demonstrations and labs and things to do. But basically, this explains rocket propulsion and all this stuff. The only other thing we have to do is conservation of momentum, which is, I think, really fun. But I'm a physics teacher, so I might not be the best. But anyway, force times time, if that causes a change in momentum, momentum is mass change in velocity, isn't it? A change in momentum, unless you change the mass, but we're not going to, right? Okay. A force times a time on an object causes a mass to undergo a change in velocity. That's what the formula is saying. Okay. And this looks like this really fancy formula, but keep in mind that it's not. It's something you've already seen before. If I rewrite it this way, force equals mass times change in velocity over time. Right? What is change in velocity over time? It's acceleration. So this is just F equals ma. But we've written it this way because that's what we do for momentum. Now, a historical note is that Sir Isaac Newton, who came up with F equals ma, really didn't say F equals ma. What he said was that force is the time rate change of momentum. Right? In fact, what he said was force is equal to the time derivative of momentum. And everybody said, what's derivative? And he said, well, that's the rate of change. And they said, what's the rate of change? He said, well, that's in calculus. And they said, what's calculus? He said, oh, I invented calculus too, right? Here's this calculus, and you got to learn that first, right? You know, and all first-year college students have hated him from then on. You know, it was a thing. Anyway, so this is what we've got, and we've got probably an example. F is force, T is time. Yes, do we know this? Right. Right, so this is in newtons, right? This is time in seconds, right? This is mass in kilograms. And this is velocity, change in velocity in meters per second. So let's do an example problem. Let's suppose we've got a batter here. Batter, right? The batter hits the ball, and the ball has a mass of 0.145 kilograms. I think that's what a baseball is, right? 145 grams, something like that, right? Okay. And the ball is going, let's suppose the ball is going this way with a velocity of positive 41 meters per second. And the batter hits the ball, and I think batters can hit the ball faster than a pitcher can throw them, can't they? So let's say that the ball goes back outward, right? In when it gets hit, the ball is flying this way, and let's make it be 53 meters per second, right? And let's suppose that we've got the mass, we've got velocities. Let's suppose that the strike of the bat actually occurs in the time is. Let's say that this is when it goes smack like that. That is, let's say that it's 0.035 of a second, right? It's 35 milliseconds or something like that, you know. And obviously they could do a time warp of it, and you'd see the bat bend, and it would dent in, and the ball would deform and wrap itself around the bat. Have you guys ever seen those shots? Yes. Those pictures or like a golf ball getting hit by a golf club, right? How it flattens out on the head. Have you seen that? It's kind of an amazing thing. Maybe we can Google image it or something here in a sec, right? But all of that takes 0.035 seconds. I'm just making this up, right? So the question here is, what's the force exerted on the bat? Yeah? And this is, by the way, the mother of all problems. You'll never see a problem this hard ever, except for like right now. Okay? So let's figure out what we know. Let's make this guy positive 41, right? So force is what we're trying to find. What's our time? 0.035, right? The mass is easy. That's 0.145 kilograms, right? What's our change in velocity, though? We have to be very careful. What is the change from positive 41 to negative 53?
Negative 94.
Is it negative 94 total? Yeah, so be very careful. Remember, it's a vector, and this ball turned around and went back the other way, right? So the change is, we got to draw a little number line here, right? Okay. It went from positive 41 to negative 53. Isn't that a change of negative 94? isn't it? Yeah, so I guess we're finding the force on the ball, which will be the same as the force on the bat except for its sign, right? So this is negative 94. Take your calculator, go this times this divided by this, and you'll get the force. Do baseball bats ever break? They break all the time, more and more, right?
Really? Okay.
This is 389 newtons of force. Yeah? It's actually minus 389 newtons. All that means is that the force is to the left on the ball, which makes sense, right, doesn't it? The force on the ball was to the left. The force on the bat would be to the right. Force on the ball is to the left. Yeah? That's not too bad, is it? This is average force. Of course, the force is probably going to be like, it's going to rise, go to some peak, go back down, right? Kind of a thing. Let's try some of these.